Hi, I'm Davide Nicolis and I'm going to talk to you about the work that my colleagues and I have done at Politecnico di Milano. We worked on the shared control of a dual-arm teleoperation system, where one robot is autonomous and equipped with a camera, while the other is teleoperated. We developed a unified visual servo controller for occlusion-free teleoperation in dynamic environments. The proposed controller relies on a quadratic programming optimization formulation that simultaneously takes into account both robot arms. While one arm is tasked with tracking the input from a user operating a master station, the camera relies on feature information to avoid occlusion and keep the teleoperated arm in the field of view. To this end, an occlusion constraint is defined in the image space based on the minimum distance criterion. The idea is to prevent the robot tool from colliding with obstacles in the environment, and thus disappearing behind them. The result is then implemented in the QP controller as an inequality constraint expressed at the acceleration level. Although we can guarantee the constraint robustness for dynamic objects and moderate uncertainties in the computation of the interaction matrices, with the inclusion of a constraint alone, it is not possible to ensure neither an intuitive view of the scene for the user, nor an optimal camera motion, due to the locality of the controller. This motivates the introduction of a switching control policy based on a finite state machine. The teleoperation task is divided into 4 different phases that generate a user-friendly camera behavior by regulating different quantities. We consider a reaching task where the user has to grasp the orange goal, while avoiding occlusions generated by the green obstacle. During the setup, the robot tool and the goal are regulated in the field of view. In the approach phase, teleoperation begins, and the tool is kept fixed in the field of view while tracking the user input in 3D. Upon activation of an occlusion constraint, the system switches to the occlusion state. Here, we regulate the occluding object area and center of mass, as well as the camera velocity along the optical axis, to ensure a proper camera behavior. Once the user is close enough to the goal, the tool is free to move in the image and complete the operation. I look forward to talk to you more at the interactive session. Thank you very much.